The first application of systems of linear equations that we are going to look at is mixture problems. Okay, mixture problems, if you're planning to go into the medical field, into nursing, into pharmacy, studying the environment, even we'll see an example of being a jewelry maker, or perhaps pool maintenance, or all sorts of things where you might have to work with chemicals or mixtures or something like that. We're going to see applications of these mixture problems. So here in the yellow box is sort of a summary of a general strategy that you can use for these systems of equations word problems. Okay, so the first step is to read everything carefully and try to restate it in your own words. Make sure you identify what the problem is looking for, and then you want to assign variables to represent your unknown quantities. And that's really important because that's always the first question is, well, what should my variables be? That seems to be where people get stuck the most. It has to be the values from the scenario that are unknown. Uh-oh, I don't want that. Remind me later. And this is often the step that people skip. It is step one for a reason. If you don't know what your variables represent, it is impossible to write an equation because we don't know what our variables are. Okay. Once you have your variables, then you want to try to write a system that models using the problem's conditions, and then we're going to solve it. And then the last step is one that we often overlook as well. We want to make sure that we kind of reflect on our solution. Does it make sense, and does it agree with the wording of the original problem? Okay. So mixture problems. Chemists and pharmacists, and like I said, like pool management, you often have to change the concentration of a solution and other mixtures. So for example, you have to keep the chlorine level of your pool a certain concentration of chlorine. And so if the chlorine is too high, you have to decide how much to add to bring it down, or vice versa. So in these situations, the amount of a particular ingredient in the solution or mixture is given as a percentage of the total. Okay, so if I said that I had a solution that was pure acid, it would be 100% acid. But maybe it is only 40% acid. That means that 40% of my liquid is acid and the other 60% is something else. So here is an example. We're going to walk through those 4 steps of problem solving here with this one. So number 5 says, a chemist working on a flu vaccine needs to mix a 10% sodium iodine solution with a 60% sodium iodine solution in order to end up with 50 milliliters of a 30% sodium iodine solution. So we have one solution that's really weak sodium iodine and one that's really strong sodium iodine. We want to mix those together to get a percentage that's kind of in the middle as far as its strength of sodium iodine. So how many milliliters of the 10% solution and the 60% solution should be mixed? And the question there is really what helps us identify our variables. The question is how many milliliters of each. So those are our 2 unknown quantities. So we're going to define our variables as those 2 items. All right. So now we want to set up a systems of equations that is going to model this problem's conditions. Now I'm going to show you the method that I like to use, which is organizing this information in a table. I like this because you will set up the table the exact same way for every single mixture problem. You just have to identify that it is a mixture problem, and then you know to set up the table this way. So here is how we are going to set up this table. It's going to have 3 rows and it's going to have 3 columns. So the rows are going to represent the 3 different types of mixtures that we are working with. So we are working with a 10% mix. We're working with a 60% mix. And we want, ideally, a 30% mix. So those are the 3 types of mixtures that we are dealing with. Now, there are 3 things that we know about these mixtures. The first is we know how many of them we have or want. So we have the number of milliliters. That's the first thing. 2 of those are unknown, but 1 of them are known, but that is still a quantity that we want to describe for each of these mixtures. We know the percent of sodium iodine in each of these mixtures. I feel like I got too many lines on my U's and M's there. The amount of sodium iodine. And then lastly is if I know the percent and I know how many milliliters, then I can identify exactly the amount of sodium iodine that is in each of these mixtures. Okay, like if I had a 10% mix and I had 100 milliliters, then I know 10 of those milliliters is sodium iodine, 90 milliliters is something else. Okay, so that's what we're talking about when we mean amount. So that is going to be the table that we're going to use to organize our information here. And so now we're going to refer back to the problem and try to fill in all of this. So for the number of milliliters, well, I don't know how many of 10 and I don't know how many of 60, but we did define those as our variables. As for the 30% mixture, the problem told us that we wanted to obtain 50 milliliters. So we know that, okay? Now, based on the types of mixtures we have, we also know that we have 10% of sodium iodine, which can be written as 0.10 or just 0.1 as a decimal, okay? We know that we have 60% in the 60% mixture, obviously. These mixtures are kind of named by their percentage, so this seems kind of redundant. But sometimes it says like solution A, solution B, or paint color 1, paint color 2. So that's kind of why it may be labeled differently on the rows. So this 60% is going to be 0.6, and then the 30% is going to be 0.3 when we change these to a decimal. Now, if I know how many milliliters I have, and I know the percent of sodium iodine in there, then to figure out the amount, I want to multiply those things. So we have 0.1x tells us the amount of sodium iodine. That's 10% of the number of milliliters. Similarly, excuse me, we have 0.6y. And then for the 30% mixture, we know exactly how much. We have 0.3 of the 50, which comes out to 15. So 15 milliliters total of sodium iodine is what needs to be in our mixture. Now, from this table, we can build 2 equations, and it's going to come from right here, the total number of milliliters, and it's going to come from right here, the total amount specific to the sodium iodine. Here's our system of equations. We know that the amount of 10% plus the amount of 60% has to equal the amount of the 30%, which we know is 50. And then lastly, we have 0.1x plus 0.6y equals 15. So the top equation shows the total milliliters of the mixture. So that's both the parts that are sodium iodine and the parts that are not. The second equation represents just the amount of pure sodium iodine. So we know that 30% of our 50, which is 15, is how much of that needs to be sodium iodine. So that's where that equation comes from. So that is our system of equations. Every single problem is going to set up with these 3 rows and these 3 columns, and your 2 equations are going to come from right there. Okay. Now, I don't want to erase this, so I'm going to go ahead and work step 3 here in orange next to my system. So step 3 is to go ahead and solve the system of equations. Now, you can use either substitution or elimination. I don't like using elimination for these problems with the decimals. I don't know why, it's just a preference of mine. So I'm going to solve this first equation by subtracting x from both sides. So if y is equal to 50 minus x, then I'm going to come down here, and in this second equation, I'm going to make that substitution. So I have 0.1x plus 0.6 times 50 minus x, don't forget those parentheses, equals 15. Now with the decimals, you're probably going to want a calculator. When we solve this equation, here's what we get. X is equal to 30. And then, as always, I want both because it asked us for the amount of each solution. So x gave me the amount of 10% mix. Now I need to take this 30 and plug it in. I know that y is going to be equal to 50 minus x, which I know was 30. So we get 20 for y. And then step 4 is look at your answer. Make sure that you have answered the problem correctly according to what it asked. The question was, how many milliliters of the 10% and the 60% should be mixed? So to answer this question appropriately, we would want to say 30 milliliters of 10% solution and 20 milliliters of 60% solution. And so that would be our final answer, and we reflect and see that we've answered the question correctly, we've used correct units, and we are good to go. So I want to show you 2 more examples just to kind of reiterate how this table stays exactly the same every single time, but we want to set it up for some new problems. I'm not going to go through and solve the systems on these next 2 examples because I don't think that's where we need the practice. I think writing the system is where we need the practice. On your homework, though, you will want to go ahead and solve these and get the answer. So here is, come on, here we go. Next example. So a chemist needs to mix an 18% acid solution with a 45% acid solution to obtain 12 liters of a 36% acid solution. How many liters of each of the acid solutions must be used? There's a nice little typo right there. So the first thing we need to do is define our variables. So x and y are going to be the number of liters of each of our 2 different solutions. Now, once again, we're going to set up a table now to organize our information and build our systems of equations. So the 3 rows are going to be the 3 types of solutions. The 3 columns are going to represent the number of liters, the percentage of acid, and the amount of acid. So the table is going to look like this. So we have our 3 types of solutions down the side, and we have our 3 characteristics along the top. So take a moment now and see if you can fill in that table yourself this time. So put the video on pause, fill out the table in your notes, and in 3 seconds, I will have the answer for you. So here is how our table should look. And we find out that our final solution should have a total of 4.32 liters of pure acid in it, mixed with, 7 point something of non-acid in the mixture. So now, using the first column and the last column, go ahead and set up your system of equations. There is our system. And if you solve this system using whichever method you care to use, you should get the following answer: 4 liters of the 18% and 8 liters of the 45%. Now you can think about this, that kind of makes sense because 36% is a lot closer to 45 than it is to 18. So it makes sense that we want more of the stronger solution because we want to keep a relatively strong solution there. Okay, so the last example here is an example for a jewelry maker. So a jeweler needs to mix an alloy, which is a mixture of metals, with a 16% gold content and an alloy with a 28% gold content to obtain 32 ounces of a new alloy with 25% gold content. How many ounces of each of the original alloys must be used? So I'm going to let you try this one from beginning to end. And if you pause your video, then I'll be back in about 3 seconds with the work for this one. Here is where you should end up. So your final result is 8 ounces of the 16% alloy and 24 ounces of the 28% alloy. And again, if you compare what we wanted with what we had, we wanted a 25% and we were mixing 28 and 16. So we really only needed to take that 28% alloy and water it down just a little bit. So that's why there's so much of the 28 compared to the 16, because we did not need to decrease the gold content by very much. And so that is our last example for today. We'll see you all soon.